Chemistry 3111, Organic Chemistry 2. This is Chapter 13, Ethers and Epoxides, Thiols and Sulfides. I'd say that the Ethers and Epoxides section covers about maybe greater than 90% of the chapter, and then 10% or less, we're going to talk about thiols and sulfides. So most of it is going to be about ethers and epoxides. So let's get started. Introduction to ethers. Everybody needs to know what an ether is. This goes all the way back to your days in early Organic Chemistry 1 when you covered all the functional groups. It says here that an ether group is an oxygen atom that is flanked or bonded to two alkyl groups. It could be alkyl groups. It could be aryl groups. We'll put here alkyl or aryl groups. Okay, either one is totally fine. And, something I like to tell my students, when you're looking at functional groups, you always have to do the 30,000-foot view. You can't just hone in on one atom and make a decision about functional groups. You got to look at the entire thing. Because if one of the R groups, for example, was an acyl group, and an acyl group is when you have a carbonyl attached to an R group. Well, if one of the R groups was an acyl group, then you'd have an ester. Right, you see this oxygen right here is attached to an R group, but then you've got a carbonyl attached to something, so that's an acyl group. And so this is an ester, not an ether. So you always want to look at the entire thing before you make any harsh judgments. So again, the R groups can be alkyl, aryl, or vinyl. And if you can't remember what a vinyl group is, so a vinyl group is nothing more than a carbon-carbon double bond coming off like that. That would be a vinyl group. All right, so ethers, we know what an ether is. Well, let's move on from there now that we know what an ether is. Where would you find an ether? You find ethers all over the place. Okay, for example, if you look at morphine, you can see that there's an ether in morphine right here. This interesting structure, and you know that other analogs of morphine like codeine, heroin, they all have an ether in them as well. And you can see, of course, that there's other cool functional groups in here. In morphine, you have a couple of alcohols, you have a tertiary amine, you have an alkene, you have an aryl. Anyhow, but you have an ether in morphine. Another place you might find an ether, or you will find an ether, is in Prozac, which is fluoxetine. That's the IUPAC name, but you can see that you have an ether in Prozac. You also have an amine over here in a couple of aryl groups. So you find ethers not only in naturally occurring products, but also in marketed drugs and vitamins. Well, how would you name an ether? Let's talk about how we name ethers. And what's interesting about naming ethers is that we actually have a couple of ways to name ethers. We have the systematic way, and that is where we just follow the IUPAC naming rules to a T. And there's another way that we name them, which is called using a common name. And we're going to start with common names. And it says here, common names are often used for ethers. And I would say here, we'll say small ethers or small-ish ethers. And if you're wondering, is there a cutoff for small ethers? No, not particularly. But I would say that if you can name the R group, you can give the ether a common name. So let me show you what that means. It says, name each R group. What are the different types of R groups that we know as chemists? We know methyl groups, we know ethyl groups, we know propyl groups, right? Everybody here should know the propyl group and the butyl group. You know an isopropyl group, which looks like this. Okay, and there's 4 types of butyl groups. There's tert-butyl, sec-butyl, isobutyl, and butyl. So you need to know all those. What you do is you name or arrange those R groups in alphabetical order, and then you end off with the word ether. If you take a look at this example right here, we have an ethyl group on one side, a methyl group on the other. Of course, E comes before M in the alphabet, so we just write the name as ethyl, methyl, ether. Over here, we have a tert-butyl group and a methyl group. Remember that we ignore all prefixes except iso, cyclo, and neo. Tert is not one of those prefixes, so we ignore it. And we alphabetize according to the letter B and the letter M. And so the name of this compound would be tert-butyl methyl ether. Just another word of note about tert-butyl methyl ether is that the acronym that people use for it oftentimes is MTBE, which is methyl tert-butyl ether. And you can see that they have these two groups put in the incorrect order. So MTBE is technically not a correct acronym, methyl tert butyl ether. However, people still call it that. It's a very commonly used ether in extractions in organic chemistry, and it also used to be used as an additive in gasoline until it found in groundwater in the northeastern United States, and that kind of put the kibosh to all of that. So there we go. Now we've covered common names for ethers. Well, how do you give a systematic or an IUPAC name? Here's what you do. You find the longest carbon chain, and that will serve as your parent. And then you look for the smaller R group, and you name that as an alkoxy substituent. So you see that in this box down here. You have the parent, which is the largest R group, and the smaller R group with the oxygen together, they make an alkoxy substituent. And so you can imagine if you have a methyl, I'll just give you a couple examples. If you had a methyl and an oxygen, that would be called a methoxy. If you had an ethyl with an oxygen directly attached to it, you can imagine that would be an ethoxy. Let's try a crazy one. If you had an isopropyl with an oxygen, that would be an isopropoxy. So propoxy, butoxy, tertbutoxy, isobutoxy, secbutoxy, right? Anyhow, so that's how we would do it. If you take a look at the example that's shown here, you can see that the longest carbon chain has 1, 2, 3, 4, 5 carbons. Therefore, this is some kind of pentane. And then we have an ethoxy group at carbon number 1. And so the name of this compound would be 1-ethoxy pentane. There we go. And you can see why we used the IUPAC or systematic names for larger ethers where we wouldn't be able to come up with a name for an alkyl group if it was, had too many branches or something. Well, with all that information in mind, let's take a look at some practice problems here. And it says provide an IUPAC name for each of the following compounds. And again, IUPAC, we're thinking about giving these systematic names. So systematic, so not common names. The only one that I could give a common name to would be this one. You have an isopropyl and an ethyl. So you would call that ethyl isopropyl ether. We can write that in after. But anyhow, let's come up with a systematic name. We look for the longest carbon chain, which has 1, 2, 3 carbons. Therefore, this is some kind of propane. It's some kind of propane. And we would number it like this, 1, 2, 3. And then at the second carbon, we have an ethoxy group. So we would call this 2-ethoxypropane, 2-ethoxypropane. Again, I'll just scribble the common name, and your common name would be ethyl isopropyl ether. So ethyl isopropyl ether. They didn't ask us for that, but why not? The next one, the longest carbon chain, again, is another type of propane. So we have 1, 2, 3 carbons. But now we've got a 2-chloro and a 1-ethoxypropane. So chloro is going to come before ethoxy because C comes before E. So we'll just write here 2-chloro. 1-ethoxypropane. And we have a stereocenter in here. Could anybody tell me, is this stereocenter R or S? I'm sure somebody figured it out while I was talking. I think I have an idea what it is. Could anybody assign the stereochemical configuration to that stereocenter? Would that be R or S?
Is it R?
Let's take a look here. So we've got the chlorine as being the highest priority because it has the highest atomic number. The hydrogen is in the back. It has the lowest priority. If we look at this carbon, it's attached to an oxygen, hydrogen, and hydrogen. And this carbon is attached to a hydrogen, hydrogen, and hydrogen. This would be our tiebreaker. Therefore, this would be second highest priority. This is third. So we go from 1 to 2 to 3. We're going counterclockwise. And so it would be S. So that means the name of this compound is S, 2-chloro, 1-ethoxypropane. And let's take a look at the last one. We have two halogens and we have an ethoxy group on a benzene ring. So this is some kind of benzene. And we want to number it in such a way that we give all the substituents the lowest possible numbers. And the ether is going to take higher priority than the halogens anyway. But either way, you'd get the right answer. So we have 1, 2, 3, 4. So that means we have two chloros. Chloro comes before ethoxy. So we have 2,4-dichloro ethoxy benzene. So let's put that in here. So we would name that as 2,4-dichloro ethoxy benzene. There you go. What if I asked you one more? Let's try another common one just for fun. So common name, I'll put that here. So what if I gave you something like this? If I said, could you give me a name, a common name for this compound? I'll give you a second to think about it. While you're doing that, I'll take a sip of coffee. And you can either type it in the chat or unmute your mic if you think you have an answer. Anybody have an idea about this one? Well, we've got an isobutyl and we've got a methyl. And so you would call this isobutyl methyl ether. That would be the common name for that compound. All right, well, let's move on from there. And let's talk about the structure and properties of ethers. It says the bond angle in an ether is very similar to the bond angle found in water and an alcohol. The oxygen atom is sp3 hybridized. We know that because the oxygen atom in an ether has two single bonds and two lone pairs, so sp3 hybridized. But it says here that the larger the R group, the more pronounced or wider the bond angle is. Check it out. If we look at the bond angle in water, we know that it's around 105 degrees. But once you go out to an alcohol like methanol, well, I know that in water, I know that everybody understands that the lone pairs kind of push the hydrogen atoms together to close that gap and make it a little smaller than 109.5 degrees. However, you have the same effect in methanol, but now you've got this methyl group, which is bulky, and it kind of pushes the methyl oxygen bond and the hydrogen oxygen bond a little bit further apart and widens that gap. But then once you get up to something like dimethyl ether, now you've got two bulky methyl groups and they open up that bond even more. And another thing that you want to remember is that since the oxygen atom is sp3 hybridized, ethers are going to be polar, right? You've got a polar bond and you've got another polar bond, and they have a bent molecular geometry in ether. And so we have a dipole going this way and a dipole going that way. And so if you tack those two arrows together, you end up with a resultant dipole like this. So we know that ethers are polar. Well, let's talk a little bit more about intermolecular forces. You remember from general chemistry, organic chemistry 1, chapter 12, we talked about alcohols relentlessly. And we said that alcohols have relatively high boiling points. Why? Because they can participate in hydrogen bonding. Here I have two generic alcohols, and I'm showing the hydrogen bonding between the two. Whichever alcohol has the hydrogen atom that's participating in the hydrogen bond, I don't know if I ever covered this with you before, but we call this the hydrogen bond donor, okay, because it's the one with the hydrogen atom. And then you'd call this one here the H bond acceptor, like that. And if you look at an ether does have two lone pairs on an oxygen. However, an ether cannot hydrogen bond with another ether. It can only act as a hydrogen bond acceptor. And so if you put an ether in a protic solvent, whether it's an alcohol or water, it can participate in hydrogen bonding. However, if you had two ethers mixed, if you had just a mixture of an ether and another ether, okay, in some kind of reaction vessel or anything kind of container, okay, well, there's no hydrogen bonding that can happen between the two, because yes, there's oxygens, but there's no oxygen hydrogen bond, and therefore the only intermolecular forces that are going to be experienced between two ethers are London forces and dipole-dipole forces, no hydrogen bonding. You see these effects of intermolecular forces that I'm talking about if we compare the relative boiling points of ethanol, dimethyl ether, and propane. Ethanol is an alcohol, dimethyl ether is obviously an ether, and propane is an alkane. And we know that propane, the alkane, has no polar bonds in it whatsoever. So the only intermolecular forces experienced between molecules of propane are London forces, and that's why it's got such a low boiling point. However, once you get up to dimethyl ether, because it does have a dipole, dimethyl ether experiences dipole-dipole forces, so dipole-dipole, and it also, of course, experiences London forces, which everything does. And that's why the boiling point is increased. Then you get up to ethanol, and ethanol experiences hydrogen bonding. It experiences dipole-dipole forces. Let's call it DD forces. And it also experiences London forces. And so, again, that's why the trend, we see that the boiling points increase as intermolecular forces increase. If we compare ethers, different ethers, even though they all experience London dispersion forces and dipole forces, the same intermolecular forces across all three of these ethers, but why does the boiling point increase as we go from dimethyl to diethyl ether to dipropyl ether? It's because of the increased London dispersion forces. Just imagine you have a second molecule of dimethyl ether, if we put that here, we can see that there's some surface area contact between the two. However, as you go up to a longer molecule, up to, let's say, the dipropyl ether, well, now you have the same old London forces between the two molecules, but you've got more of them. When we add the forces up, it becomes, they add up to a resultant force that takes more energy to separate the molecules, to get them to go from the liquid phase to the gaseous phase. Give me a thumbs up if you follow me on the idea of intermolecular forces and ethers. And of course, stop me if you have any questions. Is everybody with me on that? Okay, cool. Good. Groovy. Good. But let me tell you about some common ethers, ones that show up all the time. Organic chemists just seem to love. And those are these three on here. In fact, especially these two. These are both solvents that organic chemists love. The reason why ethers are such common solvents in organic chemistry, if you're wondering, why is that? Why do we use them as solvents? Number one, they're not protic. They don't have an acidic proton. So if you're using a really strong base, like a Grignard reagent, it's not going to deprotonate the ether. But another thing is that they're quite unreactive. In fact, there's not a whole lot of cool chemistry that you can do with an ether, okay? Yes, there's ether found in cool drugs and, cool prescription medications. However, an ether is quite unreactive. And so diethyl ether is a great solvent. You've probably seen that show up in the book. The abbreviation we use for that oftentimes is we just put ET subscript to O for diethyl ether. The next one is THF, or tetrahydrofuran. So the acronym for that is just THF. And the last one is 1,4-dioxane. Dioxane, yeah, it's used as a solvent. It can also be used for what's called lyophilization, which is just freeze drying compounds. If you compare the boiling points of these compounds, so boiling point of diethyl ether is 35 degrees Celsius, THF is 66 degrees Celsius, and dioxane is 101 degrees Celsius. The reason why I told you these two are even more popular than dioxane is because their boiling points are low enough that they can be removed by evaporation. Dioxane, if you've got something that's got a boiling point higher than water, that's pretty hard to remove by evaporation. And if anybody here has ever tried to recrystallize a compound and added too much water by accident, you know that it's very difficult to remove something with such a high boiling point, whereas either of these solvents, you can remove them quite quickly. You just set them to boiling temperature and they will just boil away very quickly. And so great solvents. We're going to skip the section on crown ethers. The reason why is not because it isn't important, it's because it doesn't show up on the ACS final. I've never seen it on an MCAT either, or a DAT exam or anything. So I'll leave that as an FYI. If you want to take the time to read the section about crown ethers, it's not very long. And let's move on and talk about how would you make an ether. If somebody asked you, I want you to make an ether and put it in Prozac or put it in morphine, how do you do that? How do you make an ether? Well, the first way I'm going to teach you to make an ether is an industrial preparation of ethers. And it says here that diethyl ether, that solvent that I told you was very popular, it is made by the acid catalyzed dehydration of ethanol. So essentially, all they do is take a bunch of ethanol and heat it up in acid and just heat the crap out of it, pardon my language, so that they drive off water, essentially, because you can see that in this step right here that you're losing water. So you could even put here minus H2O, like that. Anyhow, so you end up losing water along the way, and you end up making an ether. And I think it's important for you to know this mechanism. So I'm going to put in here, know this mechanism. And I bet you could have figured it out already. In the first step, the acid protonates the alcohol to convert it into a good leaving group. Then once it's a good leaving group, it can be attacked by a second molecule of ethanol as a nucleophile. And then we have another molecule of ethanol that can come in and remove the proton from the oxonium to produce diethyl ether. Now, this is really cool chemistry. Personally, I'm a big fan of any kind of chemistry where you just throw everything in a pot and heat it up. I mean, can't get much easier than that. The caveat to this chemistry, which is really cool, the caveat is the only real utility there is for this chemistry is to make simple symmetrical ethers. If you want to make an unsymmetrical ether, so let's say you wanted to make something with a methyl group on one side and a propyl on the other, this would not be the way to do it. Okay, you'd have to find another way to do it. And if you're wondering, are you going to show me? The answer is, of course. Of course, we're going to talk about another way to make an ether, namely an asymmetrical ether. And the way that we do that is a really old reaction that is still widely used today, and it's called the Williamson ether synthesis. It's not making a bond between carbon and carbon, so no Nobel Prize, but it's pretty cool. It's making a bond between carbon and oxygen. And another thing that students like about the Williamson ether synthesis is if you understand proton transfers and SN2, the mechanism is relatively not as complex as some of the things that we've looked at in this class. So here's what you do to do a Williamson ether synthesis. You start with an alcohol. You treat it with sodium hydride. This is your base, right? Remember, the hydride ion is not a good nucleophile because it's not polarizable, but it's a great base. And then you treat it with an alkyl halide. Well, if it's stepwise, step 1 and then step 2, what happens in each step? The first step is a proton transfer, namely, it's a deprotonation. The hydride attacks the alcohol and removes a proton from that alcohol, and then you end up making an alkoxide. Well, what do we know about an alkoxide? An alkoxide is a good nucleophile. And so when you throw in the alkyl halide, you get a nucleophilic attack, and this is just a plain old SN2 reaction, nucleophilic attack and loss of leaving group to produce your ether. However, there's limitations for this reaction too, isn't there? Because if it's SN2, this step, that means the nucleophile is going to attack the electrophile, but the only way it's going to work is if the electrophile, we'll put here, electrophile must, and I think I have this on my next slide, but whatever, must be methyl or a primary alkyl halide. If you have a secondary alkyl halide, you will get some substitution, but you'd mostly get elimination. Check it out here. I have it right here. So since this is SN2 substitution, it only works well with methyl and primary alkyl halides. Again, if you have a tertiary, you're only going to get elimination. And if you've got a secondary, well, you're going to get mostly elimination. And where does that leave us? That leaves us with some really cool problem-solving applications for me as your instructor and for you as a student in the class. And this is a real classic scenario that we like to pose to our students on quizzes and exams. Let's say I want you to make MTBE. I told you it was the wrong acronym, and here we are using it, right? Let's say you want to make tert-butyl methyl ether. Well, there's two possible ways that you could make this by a Williamson ether synthesis. You could either cleave this bond, or you could cleave this bond. Either way, one of them. So what I'm saying is if you cleaved the blue bond, then you'd be starting with this alkoxide. And if you cleave the red bond, then you'd be starting with this alkoxide. Well, let's take a look at those two possibilities. If we break the blue bond, that means you'd be starting with tert-butanol, this compound, and then you treat it with sodium hydride, and then you'd hit that with methyl iodide, and then Bob's your uncle, because this is going to work very well in an SN2, iodomethane. However, if you broke the red bond, then you're starting with methanol and you're deprotonating it. Nothing wrong with that. However, what's the problem? This is a tertiary alkyl halide. It's not going to give you substitution. It's going to give you an elimination. You're wondering, what will that elimination look like? Well, look, this is something you should be able to draw. So we have our alkyl iodide. We have a proton, and we have, I'm just drawing one proton for instructional purposes only. So what's going to happen is the negative charge is going to remove a proton. You're going to lose the iodide. That's going to give you methanol plus isobutylene. So this is only going to give you the E2 product. Useless. That's not an ether, is it? And so again, we love to ask this question where we throw a scenario at our students and we'll say, okay, we're giving you an unsymmetrical ether. What would be the best way to make it if you've got two possibilities? And you have to evaluate which bond should be cleaved and which alkyl halide you would want to use. Let's talk about another way you would make an ether. So far, we've talked about acid, the industrial synthesis of diethyl ether, which is just an acid catalyzed dehydration reaction between two molecules of ethanol. Then we talked about Williamson, and now we're going to bring in oxymercuration, demercuration. Remember this old chestnut from way back in chapter 8 in the alkenes chapter? We also talked about this reaction again in chapter 11, which is the first chapter that we covered this semester. But remember that oxymercuration, demercuration can be used to make an alcohol from an alkene. This is something that we looked at a bunch of times. And we also said, well, the reason you would use oxymercuration, demercuration is because you'd want to avoid carbocation rearrangement. But we also said that it adds with Markovnikov regioselectivity. Do you remember? And I'm not going to go over this in detail right now because we've gone over it already this semester, but hopefully you remember it passes through what's called a mercurinium ion. So the mercurinium ion. And then the mercurinium ion undergoes nucleophilic attack by water, and then it ends up undergoing the demercuration with sodium borohydride. But if we replace the water, if we replace this, we'll here replace with alcohol, right? If you replace this with an alcohol, the alcohol can attack the mercurinium ion, and instead of getting an alcohol, you'll get an ether because you end up with OR instead of OH. Check this out. I have it on the next slide here. It says similarly, alkoxymercuration, demercuration can be used to synthesize an ether. Excuse me. Here's our ether. Carbon, oxygen, carbon. Pretty cool, huh? All you have to do to get this reaction to work is use mercuric acetate, and instead of water as your solvent, use an alcohol. You can even choose your R group. Let's say you want a methyl group here, you would choose methanol. Let's say you wanted an ethyl, you would use ethanol, so on and so forth. Of course, it's going to have its limitations because you've got to choose an alcohol that would be able to solubilize your reactants, but it's a pretty cool way of making an ether and a good use of oxymercuration, demercuration, which up until now we only used to make a to make a alcohol? Well, with all that in mind and in our head, let's talk about some questions here. It says, show the reagents that you could use to prepare each of the following ethers via a Williamson ether synthesis and explain your reasoning. All right, let's take a look. We have an unsymmetrical ether. The first one, and we could either break the blue bond or we could break the red bond. If we were to break the blue bond, then our starting alcohol would be this compound. And then we could treat that with sodium hydride in the first step. I'm just going to draw the intermediate for fun. So we'd end up with this alkoxide. And then we're going to treat the alkoxide with the alkyl iodide. It would be 2-iodopropane or isopropyl iodide. So we'll put here. And you could choose the bromide or the chloride. It doesn't matter. But what's that going to give you? This is a secondary alkyl halide. It's mostly going to give you elimination. Okay, so it's mostly going to rip off a proton to give you mostly propylene. That's not very useful, is it? If you're wondering about the mechanism, of course, it's just a regular old E2 where it's going to rip off this proton, form the double bond, and lose your leaving group. So that's not very useful. Again, this is the E2 reaction, and the reason why is because this is a secondary alkyl halide. Now, what if we were to break the red bond instead? Well, in that case, you'd be starting out with isopropyl alcohol or isopropanol. You would treat it with sodium hydride, our base, in the first step. You should know how to draw the reaction mechanism of the hydrogen abstraction, or just the deprotonation, I should say. So let's draw that out here. Because something that I didn't point out is that this reaction is irreversible. And the reason why is because when you form your alkoxide, let's draw that alkoxide. Not only do you get the alkoxide, but what's the other product? You get hydrogen gas, right? And hydrogen gas is just should come out as bubbles. So this reaction is extremely irreversible, never going backwards once the hydrogen leaves. Anyhow, so you make hydrogen gas, and then now your alkyl halide is going to be this, where we have our 6-membered ring, yes, but then you have the methylene, and you have an iodide here. So this is a primary alkyl halide. We could do the Drake meme, for this one, you have Drake with his orange coat pushing his hands away and turning his head, whereas this one, Drake would still be in his orange coat, but giving it a big thumbs up and a smile. And so our nucleophile attack the primary alkyl halide, and that is going to give us our product. So here we go. Now we've got a winner way of making this unsymmetrical ether. So what would we call them? I don't know. A bad and good? I don't know. But either way, the first strategy will not work. The second one will work because the SN2 is highly effective on a primary alkyl halide. Let me see here. Just give ourselves some more space. So let's zoom in on this unsymmetrical ether. Look, I got two possibilities. Would you want to start with, I'll just give you the two possibilities. Would you start with methanol as your starting alcohol, or would you want to start with this tertiary alcohol? Could anybody tell me which one would be the best starting alcohol, methanol or the tertiary alcohol? Remember, we want to do an SN2 reaction. Anybody? Methanol or the tertiary alcohol?
The tertiary?
Yeah, that's what I would pick. Yeah, absolutely, right? Because then you're going to have methyl iodide as your electrophile, which is going to work just perfect for an SN2. If you had chosen methanol, then you'd have to have all of this as your alkyl halide. I mean, that's tertiary. That's impossible. That will not work at all. That will only give you E2. So great. Perfect. Let me just start by erasing this, and we'll write down what the strategy would look like. So let me just zoom out. But perfect answer. Great. All right. So let's start out here. Let's draw our tertiary alcohol. This. And in the first step, we're going to treat that with sodium hydride. That's going to give us this alkoxide, which is going to be a great nucleophile to react with iodomethane. Here we go. We're going to do our, oops, where's my, there we go. We're going to do our SN2. So 1, 2, like that. And that's going to give us the desired product. Perfect. There you go. And again, I've taught this class long enough to know that this is a real classic. Organic chemistry instructors love to ask this question. They love to ask it on the ACS final. Dr. Diaz's sister wrote the DAT exam maybe 2 summers ago, 3 summers, I can't remember. But she borrowed my desk in the office to do it. And I had all the DAT materials, and we would look at them sometimes. And this would be another one. If you're thinking about going to dental school, they love to ask this question. Great question. Let's try that alkoxymercuration, demercuration, wherein you use an alcohol as a solvent as opposed to water. So if you weren't quite sure about how that would work, I'll show you right here. So let's take a look at the first alkene. And this is an unsymmetrical alkene, right? You've got 2 hydrogen atoms here, and you have none on this carbon. So the rich are going to get richer if you add the hydrogen and the ethoxy group in a Markov-Nikov fashion. So what's that going to look like? What it's going to look like is this, is that the first step, you're going to add mercuric acetate. And this is not a mechanism I ask you to, write out or anything. And then you would use ethanol as the solvent. And then in the second step, you just use sodium borohydride, and that's it. So again, I have the ethanol written in blue, and that's because you're adding this part and this part. If we look at the next one, same rationale, it's going to be a Markov-Nikov addition. The rich are getting even richer in hydrogens. You can see that you're adding, maybe I'll use, I don't know, I could use my green pen. I could give that a shot. You're adding this and this over here. And of course, you still have this proton. So what's my solvent going to be in this case? Could anybody describe the solvent here or name it? It's not one that we look at a lot. So if you're thinking, oh, that's something weird, All right, all you have to do is kind of play a game of connect the dots. You've got this group, right? You've got the square, the cyclobutyl with the oxygen, and then a hydrogen. So it would be cyclobutanol would be the solvent, not one that we see a lot. That would be your solvent if you wanted to add or form a cyclobutyl ether off the side there. Kind of a cool reaction. So very neat reactions here, these alkoxymercuration demercurations, wherein we use an alcohol as a solvent as opposed to water. And the reason we do that is because we can make an ether. Very interesting chemistry. At least I think it is. Well, let's keep on moving along here and talk about some more reactions of ethers. So some more reactions of ethers. And something that I told you before is that ethers are actually kind of unreactive. However, most compounds, if you hit them hard enough, they will react. And ethers are no exception. It says here that you can cleave an ether or break it apart using acid. So as ethers will undergo an acid-promoted cleavage. You have to use a strong acid. Usually, it's usually done with HI or HBr. Those are the best acids to use. Okay, and it's a mechanism that I actually expect you to know. And let me just show you what the net result is first. It's not written in that order in my slides, but let me see here. I can squeeze it in here. So what you do is you take an unsymmetrical ether, or it could be symmetrical, it doesn't matter. But let's say you had unsymmetrical ether like this, and let's assume that both of these groups are alkyl groups. Alkyl groups. You take it and you treat it with a strong acid like HI or HBr. You use excess HX, and you heat it up. And what that does is it gives you 2 alkyl halides. It'll give you the R prime attached to the halogen. It'll also give you the R double prime attached to the halogen. And if you're wondering, well, where the hell's the oxygen? The oxygen gets lost in a molecule of water. Now that is what I have written on this slide right here. So let's take a look at the mechanism. And I bet you that this is one of those mechanisms that if I told you to sit down with a blank piece of paper and said, see if you can figure out what the heck is going on here, I bet you could figure it out without my guidance. Check it out. The first step is nothing more than a proton transfer on the oxygen of the ether to convert it into an oxonium. But what that does is now that you've got the positive charge on the oxygen, it sucks electron density away from the carbon, which renders both of the carbons more electrophilic. So now a halide can come in as a nucleophile, and we get an SN2 reaction to form the alkyl halide from here, and then you're left over with another molecule, or a molecule of the other side as an alcohol. So now you can probably guess what happens. That alcohol gets protonated by the strong acid. You convert the alcohol into a good leaving group, water, and then you get a second SN2 with a second molecule, or sorry, a second halide ion to form the second molecule of RX. So this is the first RX group, this is the second one, and here's your water. Again, this is what I was showing you right here. You form the RX, RX, and water. And that's what happens when you do an acid-promoted cleavage of an ether. Kind of neat chemistry. And I'm going to put down here, you must, put here, must know this mechanism. Got to know this mechanism. It's a very important mechanism in organic chemistry, the acid-promoted cleavage of an ether. Well, like most things in organic chemistry, I teach you something. You know, I had a student a number of years ago. The guy was pretty funny, and he used to say, Mr. Dion, it seems to me that organic chemistry is nothing more than me learning a bunch of rules and then the exceptions to those rules. And I said, well, you got a point there. I can totally see your point. And there is an exception to this acid-promoted cleavage, and that is, first of all, if you have a tertiary group, it doesn't go by an SN1, an SN2, it cleaves by an SN1, but that's neither here nor there. The main thing you got to know is if you have an aryl group or a vinyl group. So we have an aryl group here, so just an aromatic ring or a vinyl group. So that would mean something like this. So this would be a vinyl group. Those will not break apart to give you RX. They will just give you an alcohol. So if you use an aryl ether, it gives you a phenol. And if you used a vinyl, it would just give you this vinyl alcohol, okay? You will not blow apart that side of the molecule. And if you're wondering, why wouldn't that work? It's because you can't have partial positive charge on an sp2 hybridized carbon. It just won't work. And so it doesn't break apart. Anyhow, sorry. You can't do the SN2 at an sp2 hybridized carbon. Sorry, I misspoke. Mr. Dion needs more coffee. Okay, and so that's a major exception, but it's one that I could ask you on a quiz. In fact, if you look in a few minutes, I have a question about that. In fact, why don't we do it right now? But before we do, I'll just mention a quick thing. You don't have to know really about auto-oxidation. The only thing I ask you to know about auto-oxidation is, so diethyl ether, I told you it had a really low boiling point, right? The boiling point we said was what, 35 degrees Celsius? So extremely low boiling point. And the thing about diethyl ether is that it can be stored at in a lab in an amber bottle or something. But if you leave diethyl ether out long enough, it will develop peroxides. So ethers will react with oxygen in the air and they form these hydroperoxides. And the problem with those hydroperoxides is that they're explosive. So the first job that I ever had in big pharma was working as a medicinal chemist, but I had a little side job where a couple times a year I would have to go through the entire chemical collection, which was, thousands of compounds, and test all of them for peroxides just to make sure that nothing was going to explode or anything. Around the department, we generally frowned upon explosions. But anyhow, that's all I really expect you to know about auto-oxidation. There's a section here that talks all about the mechanism, of the initiation, the propagation, and the termination, but I will not be asking you about that, so don't worry about the mechanism. Well, with all that information in mind, let's try some practice problems. This is where I find, students do their best learning is just practice. It says predict the products for each of the following reactions, and maybe we'll even give a mechanism a try here. So the first one is diisobutyl ether. So this is diisobutyl ether, just a little nomenclature practice. And we're treating it with excess HBr and heat. Keep in mind that an isobutyl group and an isobutyl group, they're both alkyl groups. And so what we're going to end up with are two molecules of isobutyl. So here's my isobutyl bromide. So we'll put times 2, plus we'll also end up with a water molecule. Now that's all well and good, but I think it'd be worth a shot for us to try the reaction mechanism. And so I'm going to switch over to a blank document here just for a second, and we're just going to give this the old college try. So this is, let's see here, we've got our isobutyl, oxygen, then another isobutyl group here, and we're treating this with HBr, right? And of course, we're heating it up. So let's start with a proton transfer. So we're going to convert one of those alkoxy groups into a good leaving group. So now we are going to draw out the oxonium, which is going to look like this. We've got our positive charge here. Now we've got the bromide, which is a good nucleophile. And we've rendered those alkyl groups more electrophilic. So the bromide is going to come in as a nucleophile like this. We do an SN2 reaction, and we end up with our first molecule of isobutyl bromide, plus we're also going to end up with isobutyl alcohol. Now that's going to react with a second molecule of HBr. Remember, we have excess, and so the alcohol is going to undergo a proton transfer. The HBr, we convert the alcohol hydroxyl group into a good leaving group. So now we've got this good leaving group, and we've got a second bromide, so bromide, which can come in as a nucleophile. Do another SN2, and there you have it, folks. We end up producing a second molecule of isobutyl bromide, and we also lost water in there. And so these are all of our products. We form isobutyl bromide, and water. And that is the mechanism of the acid-promoted cleavage of a dialkyl ether. Well, now that we've seen the mechanism, let's go back to that problem and let's try the next one. This is THF, or tetrahydrofuran. I'll just put the acronym for fun, THF. And if you hit that hard enough with hydroiodic acid, it is going to blow apart. Right? This is your R group on one side, and this is your R group on the other side. They're tethered together by 2 carbons. And so we're going to have 1, 2, 3, 4 carbons. On one side, we're going to have an iodide, and on the other side, we're going to have an iodine. And then we're also going to form water. So we form 2,4-diiodobutane and water. And in the last one, I have a question for you. If I highlight this bond in yellow and this bond in green, could anybody tell me which one of those bonds is not going to break no matter how hard I hit it with HBr? Would it be the yellow one that stays intact or the red one? Which one will not break?
The green?
No, it's not the green. It's going to be the yellow one. Whenever you have an aryl group, the aryl group is always going to stay attached to the oxygen. It's never going to break. You could make a Rick, what's that guy's name? Never going to break your bond. Never, I don't know. But anyhow, you could, all I can think of is Rick James, but that's not him. But anyhow, I digress. You can't break that bond, Lindsay. And the reason why is like let's say you protonated this with a strong acid. This is an sp2 hybridized carbon, and a nucleophile cannot come in and do a substitution reaction on an sp2 hybridized carbon. It doesn't happen. It's got to be on an sp3. So this carbon is sp3 hybridized, and so our bromide, which is our nucleophile, the bromide can come in and attack over here like this. And so the products that we would get from this reaction would be phenol, so phenol, this, and we would also get ethyl bromide. You don't get water. But to recap, if we go back to that example that I put way back here, okay, what I have shown right here. Okay, so this is two alkyl groups, but if you have an alkyl group, we'll put alkyl and an aryl group. So we'll say R triple prime, and we'll call that an aryl group. You know what? Why don't we just draw an aryl group? That would make more sense, wouldn't it? If we have an aryl group and you treat that with excess HX, son of a God. Okay, anyhow, I lost everything that I just wrote there. So, Caitlin, that's why I don't post my slides, because my iPad just hates me. So here we go. And here you would end up with phenol and ethyl iodide, like that. All right, so what I was trying to tell you is that if you have an R group that's alkyl and you have an aryl group, and you treat this with excess HX and you heat it up, you end up with RX, but you also end up with phenol. You'll never get an phenol. You do not get an aromatic ring with a halogen attached to it. Okay, so that's the caveat, or that would be the exception that I was trying to draw on the other slide. Okie doke. Well, let's move on from there. And let's talk about nomenclature of epoxides.